Hello, everyone. Welcome. This is the IEEE at Home Blockchain Series 2021. So thank you for being here today. This is the first session completely dedicated to blockchain and healthcare. And joining us today, we will have two speakers, Marco Oliveira and Tomás Honório Oliveira, and they will be presenting what appears to be their results of 1 year dedication to their master thesis. So I will leave the short introductions to both speakers, and without further ado, Marco, can you share your screen?
So today I am going to do a presentation about digital health certificates on Hyperledger Fabric. So first of all, I will do a little introduction to give you a little introduction about what I'm presenting. So my name is Marco Oliveira. I'm currently a blockchain developer at Void Software, and I'm also taking my master degree on computer engineering and mobile computing. Today, first of all, I'm going to talk about how digital health certificates work and why we are using digital health certificates. Also, we'll dive in common implementations that are currently used. And after this, I'm going to talk about my master project and the proof of concept that I am currently developing. Also, I want to thank to my mentors that helped me with this project, Catarina Reis and Marisa Maximian. So without further delay, I'll move to the project objectives. And when we started to develop this project, we have 4 objectives in mind. First of all, we entered to conduct the core state of the art about the permission blockchain infrastructure that currently exists and the digital health certificates that are implemented in the market. We also want to set up a permissioned blockchain. We want to identify the requirements to design and develop the system. And when we want to implement a proof of concept for a immunity passport pledge. So why we are using digital health certificates? Why we don't use just the paper ones? What these digital health certificates can do or do better than the paper ones? First of all, and I think the most relevant one, is that they provide a digital validation system that can be performed by anyone. So anyone that have access to a verifying system can verify that certificate is valid. And this is probably one of the biggest, one of the most relevant things on digital certificates. Also, we can share a standard across different nations in a better way that we can share if it is just a paper document. And the validation we can do is much faster than if you are validating a paper document. In a matter of seconds, we can validate that this certificate is in real true. So it's also harder to falsificate. It's not totally tamper-proof because we can exploit some bad implementations on these digital health certificates and falsificate one, but it's much harder than to falsificate a paper document. And also it's much easier to transport. We can save it on our smartphone, we can save it on the cloud and access from another device. It have an ease of transportation. So for these digital certificates, we have already a lot of existing solutions. We have governmental solutions. I think the most known one that everyone here must have some idea at least is the European Digital COVID Certificate. That it was before, it was known as the Digital Green Certificate, but now they changed the name because green, I don't think it makes any sense. So also for India, they had the CoWIN, that is another governmental solution. We have Immunity, that from Malaysia, that are also accepted in Singapore, and we have also private solutions. There is a lot of private solutions, mostly because the United States of America didn't implement the governmental solutions, and then a lot of these solutions appear on the market, such as the Common Pass, the IATA Travel Pass, the Hawk Pass, and the IBM Digital Health Pass that was already implemented, and they did a new version especially for COVID. So what now we are going to dive a little bit deeper on the digital COVID certificate, the European. This certificate provides a proof that that the person is vaccinated or have been tested or recovered from COVID. The basis of this application, it's a public key infrastructure, and the way this works, you can see on the image on the image on the right, is that we have the national backends on the bottom. So these national backends generate the certificate, and then they share the public key with an European gateway. So this public key is then fetched by another national backend from another country, and then they can check, because every country have a validated application, they can fetch the public keys from the European gateway and verify certificates issued by another countries. So further, we can see in more detail how this works. On the left, we have the country A, that is the issuer of the certificate. It gets the data from the patients and generates a certificate using a sign key service and the certificate issuance service. Then they share the public keys with the gateway, with the public key director. And then these keys, we can see that going to the right, where is the country B verifier that will fetch and use these public keys and can perform offline verifications. So as this is a public key infrastructure, we can do offline verifications. At these dashed lines, this is for further future implementations. In the future, they want to implement online verifications. So this system is not bulletproof. As you can see on the right, we have a fake but valid certificate that is issued with the name of Mickey Mouse. If you have a verifier application, you can scan the QR code and you can see this certificate is still valid today. This is an issue that happened this week. It's still under investigation, and it's not totally sure why this happens, but the preliminary investigation indicates that this is an issue with the national backend implementation. I think it was from Macedonia, because going to the last point on the slide, multiple national backend implementations that can generate certificates. So each member of the EU Digital COVID certificate do his own implementation. So, and this own implementation can generate certificates. So I think it was exploited in a vulnerability on the Macedonia backend, and they generated this fake certificate. There is another fake certificates appearing on the internet. I think you can check them. Sorry. So also another threat to this implementation is the failure to properly protect or store encryption keys. This is very unlikely, and they are security in the hardware models, at least for this implementation of the European Union. We might have weak keys that might be calculated using cryptanalysis techniques. That is also not very easy to do, but it's possible. And this is the threats for the EU certificate. So moving on to our implementation of the Immunity Passport Ledger, we will have three main actors. The health organizations that will be responsible to issue the certificates. We have the verifier organizations that will verify certificates validity. it will be typically one verifier organization, and we'll have multiple health organizations. And we also have a statistic organization that will perform metrics. For example, we'll calculate the number of people that already have the certificates. We'll check the number of people that have for example, the certificate expiry in 1 month, that kind of metrics. We also have a set of rules defined. So we need interoperability in the system. So the verifiers should be able to verify any certificate issued by any health organization. This is the main rule. So everyone can check the certificates issued by any health organization. We also have the sensitive user data should be only visible to a certificate issuer organization, because we don't want to share user data with other countries. And also we implemented, we should keep a immutable record of certificate emissions and have a validity date system to keep the record of the expired certificates. Moving ahead, to accomplish this, we are going to use a permissioned blockchain. I don't know if you know what this is. You must know public blockchains when everyone can connect to a public blockchain and is seen and act as equal. Everyone can do a transactions and anyone can see these transactions. This is not the case for permissioned blockchains. On permissioned blockchains, we have a restricted participation. So we need permission to become part of the network to interact with the ledger. Typically, there was some sort of governance structure on these networks that defined the endorsement policy for new participants join the network. And to invoke smart contracts, we'll go explain this ahead. So this is partially decentralized because the data is only on the members that joined the network, and we have much more efficient and scalability when compared to public blockchains, because we use computationally inexpensive consensus that compared to proof of work are much quicker, and we have much more scale without the resources that are used in public blockchains. So using a permission blockchain that is Hyperledger Fabric, that is a permission blockchain that contains all the characteristics that we mentioned on the previous slide, that this blockchain is permissioned and manages the membership identity, that manage ID and authentication participants of the network, and also by the access control lists that provide an extra layer of permissions that, for example, we can define roles. So we can define who can execute the chain code of the network. Chain code is the code that is executed to perform modifications on the ledger. So if we want to create an asset or modify an asset on the ledger, we invoke the chain code. So the Hyperledger Fabric, in the Hyperledger Fabric, we have two node types. One of them is the peer node that execute and verify the transactions. And we have the ordering nodes that order and propagate these transactions. We also have a ledger that have two components that where we store the data, that is a blockchain log that stores the immutable sequence record of transactions in blocks. So, and we have the state database to maintain the current state of the blockchain. So if you think about Bitcoin, in Bitcoin, we know the current state of a wallet. We know how much Bitcoins we have on the wallet going back on all of the records. Here we have a state database that keeps that current state saved on the database, so it's much quicker to access this data. So we also have private channels that gives a path for restrict messaging between the members of that channel. So now we have a system context diagram for the application. we are implemented for the proof of concept, that it is a citizen. If we go for the bottom path, we can see that the citizen go to a test or vaccination center to get vaccinated or tested and will get the QR code. So on this center, there is a health professional that will store the data of the user using the health organization application that implements the Fabric Client SDK. This Fabric Client SDK is used to authenticate on the Immunity Passport ledger and also for invoke the chain code. So that's what the application do, invokes the chain code, and we have we receive an identifier and generate the QR code. We will explore this later on the presentation. So on the top path, we also present the QR certificate. The Verifier mobile application will read this QR code, will decode it and send it to the Fabric gateway that implements also the SDK. This will be a public gateway, so we'll explore this later. And we'll invoke and return the response and validate the certificate. So explaining the concept for the Immunity Passport ledger for the Fabric network, we have multiple peers. Each peer represents an organization. We have a peer, for example, for the health organization, a peer for the Verifiers organization, and a peer for the statistics organization. They all are connected to a channel, and each of these peers can have a ledger with the status of the network. So this ledger saves the blockchain log and the state database, and the Verifier organization. For example, we have applications that are outside of the Fabric network that implements the certificate authority to authenticate on the network and invoke the chain code. We also have an orderer that order and propagate the transactions. We have network policies and channel policies down there that is used to define the rules on the network. So moving ahead, if we want to add a new, for example, if you want to add a UK health organization, we'll create a new peer for this organization, and it's simple to add new organizations. And now for the health applications, this explains all the health applications work. Typically, a health professional perform a medical action of test or vaccination and fill in the certificate creation form. The system has personally identifiable information. So the health number is not stored on the ledger. This health number is hashed before and then is stored on the ledger. The chain code will save the data on the ledger and return an hash that will be identified. That will be an identifier for that record, and the system of the health application will generate a QR code that will the system generate a QR code certificate that contains the information of the identifier for the certificate record, the health number, and the salt used to hash the health number that is sent to the ledger. So the QR code is sent to the ledger, is sent to the user, and can be used on digital or on paper. For the personally identifiable information, we only store an hash. So this makes it possible to identify a person looking at the entry on the ledger. This sensitive information is only saved on the QR code together with the salt that is used to generate the hash. So we are not keeping record of this information on the ledger. It's only an hash. So this is the QR code that we are generating. It contains the issuer organization identifier, contains the hash identifier of the ledger that will be used to search on the ledger, contains the health number, and contains the salt used to hash the health number that is on the ledger. So this is the aspect. This code is base is 64 encoded, and this is the code that will be scanned by the Verifiers application. This Verifiers application will scan the QR code and will be sending a request to the gateway of the Verifiers application with the hash identifier on the ledger. So we are only sending the hash, the identification hash of the ledger. We are not sending alt number. So we are not passing any personal information on the user on the network. So we'll get this information and we'll invoke the chain code, and on return the chain code, if the certificate exists, on return the chain code will give us the alt number hash that is registered on the ledger, and also the validity dates. So the mobile application will perform this validation offline. It will check if the QR code that have the alt number and the salt used to hash the alt number that is on the ledger will verify offline if they match, and will verify also if the validity date is correct. So we are doing this validation offline. We are not passing user information on the network. And if all the checks are okay, the certificate is valid, and the number of the alt number will be shown on the screen, and we can compare with another identification documents. So moving on, for the next steps for this application, will be finished the implementation of the proofs of concept that I presented today. We need to test also the performance of the network on a real scenario. We'll be using a benchmark tool for Hyperledger known as Hyperledger Caliper. We also will be implemented a way to protect the gateway. Since the gateway will be a public endpoint, we need to protect this against abusive and attacks, abusive use and attacks. So, okay, this is all, and thank you very much. I think I already passed the time. Sorry. Thank you very much for your attention.
And now with us, we will be having Tomás Honório. That will be, he is also a student of a master's, and he will be speaking a little bit about his work regarding contract tracing on Hyperledger Sawtooth. So I kindly ask Tomás to introduce himself also, okay? So Tomás, you have the floor.
Okay, hi everyone. My name is Tomás Honório Oliveira. I'm a master's student also, and I work at Marco Oliveira. I did this presentation with the help of Catarina Reis and Marisa Maximiano, and I'm grateful for that. And yeah, in this session, I hope to explore contact tracing and the contact tracing issues that we saw in some popular approaches in the past, and propose an architectural change by using Hyperledger Sawtooth to address these issues. As the motivation for this presentation, I can point out the global health crisis. As everyone knows, there is a pandemic that no one was prepared for at the time, and this resulted in millions of casualties and even more infected. For the longest time, we didn't have a treatment or a vaccine being necessary to rely on non-pharmaceutical methods, such as social distancing, case identification, and contact tracing. Even now, in countries that for multiple reasons don't have the infrastructure or don't have the means to inoculate the majority of the population, this is still an issue that still stands. And even in, for example, Portugal, countries that have a high degree of inoculation, this is still an issue because of new variants that may or may not make the vaccines available not as efficacious or as good in the long term. One example of this is, for example, the Delta variant. With that said, according with the World Health Organization, in order to do a successful contact tracing operation, it is suggested to locate / quarantine around 80% of the contacts within 3 days of the first case. To achieve this, we can boil down the process to three steps. The first one is identification. When we confirm that an individual is indeed infected, all of his contacts need to be identified, followed by listing. Everyone that comes into contact with said individual needs to be marked as a contact and informed of their status. And at last, follow up. We need to observe the quote unquote contact in order to monitor for symptoms. With that being said, contact tracing, it's hard, especially manual contact tracing. These methods are usually slow and not very efficient, especially for large scale endeavors. Don't get me wrong, they work and they can be helpful, but require a huge amount of resources and manpower that a lot of times is very hard to get. In order to combat these issues, many countries and institutions try to develop digital contact tracing applications, being the idea behind these that the cost of development was a lot smaller than the gain that they may have if we had high enough adoption. With this in mind, manual contact tracing is still needed. There are multiple instances. For example, if the users don't have a smartphone, and this is especially true in developing countries, that we cannot rely on digital contact tracing. So the better approach is, without a doubt, both having manual contact tracing and digital contact tracing, so each one can fill for the gaps of each other. Using digital contact tracing applications will also provide better data quality, okay? And that's one of the big factors, because if we want to have effective countermeasures, we need to know what is happening and how is happening. That was not always the case. For example, in manual contact tracing that heavily relied on memory or asking each one of the users who has he been in contact with. Despite all of this, and knowing that contact tracing or digital contact tracing can be great, it left a lot to be desired, being probably the biggest issue that he had, the overall lack of trust that this kind of applications gave to its users. To better understand why in a lot of countries, contact tracing applications never really took off or lost the majority of users in the span of a couple of months or even a couple of weeks, we can give the example of the Portuguese application. Like most of these kind of applications, it works with proximity tracking using Bluetooth. In order to work, we need to have two users and two applications. They will share ID if the users are within close contact for an extended period of time. And these are random IDs that are generated by the application. And once shared, they are stored locally, both the IDs. Every ID is stored on the smartphone for as long as is deemed relevant. It usually usually is for about 14 days, since this is roughly how long it takes until the first symptoms to appear. Until now, nothing special. The information is stored locally, and the IDs make it hard to track the user. However, the privacy concerns start with the identification of an infected individual. This is, if an user is marked or seen as infected, a health professional will be responsible to give him a code that, once inserted in the application, allows the user to share this information into the cloud, with or without some metadata regarding risk. But yeah, the problem is this system and of this infrastructure was developed was developed with base on the exposure notification system developed by Google and Apple, being this probably their most critical aspect at the time. It boils down to a single or maybe a single point of storage that relies on technology developed by Google and Apple, and overall this is not good for data privacy, and it's a big no for data privacy, especially since both of the companies already had their fair share of issues regarding privacy. On the same note, as if this wasn't enough, the state at the time also tried to push for its mandatory use, what didn't help an app that was already being criticized by the opaque data privacy. That being said, this is not the only issue. The application also had lack of coordination. There is multiple newspapers regarding that the users and even the staff, the health staff, had issues generating or getting the codes for the application, and so on. With this, the question that stands is, how can we improve this? And can we improve this by making the application more transparent? I think that we can improve at least the trust issues by making the application more transparent. The points that we need to follow up to achieve this are the first, data transparency. It needs to be clear where and how the user data is being used. Individual control of data. It needs to be clear what data is being shared and how to choose it. And a decentralized chain of power. We cannot rely on the goodwill of companies like Google and Apple that at any given point may change the rules and impact the whole system. That being said, distributed ledger, for example, a blockchain seems a good fit. As a quick introduction, the concept of distributed ledger has been gaining a lot of attention over the past few years, in part because of emergence of new technologies based on Bitcoin and Ethereum. And although Bitcoin and Ethereum are pretty popular, more than ever, blockchain is not only Bitcoin and Ethereum. We also have other
aulas, ou não?
Okay. Bitcoin and Ethereum are pretty popular. However, blockchain goes far beyond that. Examples of these are something like Hyperledger. Hyperledger is an umbrella project focused on developing tools, frameworks, and libraries for enterprise-level blockchain implementations. Some of the most well-known projects that resulted from these are, for example, as Marco mentioned, Hyperledger Fabric, in this case, Hyperledger Sawtooth, and many, many more. The use of distributed ledgers to solve trust issues was also the idea behind another application that was developed. Its name was VipTrace, and just like the Portuguese application, it did contact tracing by using Bluetooth. It worked the same way. It generated IDs, and if the users were within contact for a large amount of time or enough time, it would share the IDs. This was their active mode. They also had another feature that was doing contact tracing using GPS. This was their passive mode. That being said, the standout feature of this application is not this, but instead its use of a distributed ledger to store the information. In their case, they use a direct acrylic graph-based solution, also known as DAG. This is a different type of blockchain that aims to improve. This is a different type of distributed ledger that is not a blockchain that aims to improve speed, scalability, and cost. When we compare this solution versus chain-based solutions, we can recognize some key differences. For example, because of the adoption of the graph structure that the DAG solution has, it can process transactions in parallel. That's in direct contrast with the old blockchain solutions like Bitcoin and Ethereum that were serialized in the transactions. On the other hand, chain-based solutions offer immutability, transparency, but lack much thanks to the way they are transactions and to the consensus algorithms, lack the performance that comes. I talked about algorithms. The main issue with these is they often make use of algorithms like, for example, proof of work that is very expensive and wastes a lot of power and electricity. This one of the most one of the biggest critics nowadays of these implementations. This establishes them as not the best solution for high volumes of transactions. There's always that fun example that Bitcoin, comparing Bitcoin with the transactions of a bank, where Bitcoin has only a fraction of the capacity to handle the transactions that a bank does nowadays. That being said, the direct acrylic-based solution also has some downsides. This is because although it offers better scalability and also reduces / avoids the fees that come with many of the old consensus algorithms, it is more vulnerable to attacks. That's why many of these implementations rely on centralized features, like, for example, central coordinators, pre-selected validators, witness nodes, or completely private networks. That being said, we decided to do a small proof of concept also, that much like the one done by VipTrace, also use the distributed ledger. In our case, we choose to use or to end with Hyperledger Sawtooth, being the standout features that sold us on it, the freedom when choosing the permission level. We can choose either a private or a public network. The vast amount of consensus algorithms that it supports, because it supports dynamic consensus algorithms, parallel processing of transactions, what results in greater performance, allowing for high amount of transactions to be feasible. And at last, it provides SDK with support for multiple programming languages, abstracting a lot of the work. The application, like the ones before, also used the proximity tracking to know what user has been in contact with who. It relies on Bluetooth as well, that like the ones before, if the user is in proximity, it shares random IDs, the IDs are stored for 14 days. The different feature is the way it stores the application when a user is deemed as infected. If a user is deemed infected, it will contact the validator node by doing a request to the REST API. After this, the request will be validated by the validator that if everything is okay, will pass the information to the transaction processor. Transaction handler, sorry. The transaction handler is what contains the business logic of a particular family of transactions, and for this purpose, we can see the family of transactions as the way Sawtooth implements smart contracts. Okay, they offer vast amount of versatility in the way it works. We can define if we want more or less flexibility and also risk in our application. After everything is said and done, we need to make sure everyone that was in contact with the infected user is notified. This is done with the help of a neat feature called Sawtooth events. They occur when a block is committed and result from the validator broadcasting an event when the commit operation succeeds. With this, we can understand exactly what was changed inside the ledger, and if we want, we can fetch only the information that suits our needs. We can, for example, define what was the last block that we listened to, and fetch all the information since then. Once the information is added to the ledger, everyone can check it, as is the most case for this kind of applications. And if a user finds one ID that's also stored locally, it will first compare it, yeah, but if it finds an ID, it will send a notification that the user should get tested. Although it's impossible to say with certainty that by using a distributed ledger, we can solve the trust issues, the use of Hyperledger Sawtooth on paper solves many of the key issues behind the trust issue. That's the big issue. All this with the added benefit of being way more performance friendly that all the implementations like Bitcoin or Ethereum, and also don't rely on a single point of failure, or like, for example, DAG solutions or direct acrylic graph-based solutions to avoid the ill attention attacks. And with that, I finished my presentation. The only thing I have to add is what I would do next would be first the way the information is being stored. At the moment, the IDs are stored on the chain, and that's not the best approach. Probably off the chain approach would be better. And yeah, that's it.
Thank you for joining us, everyone, and we'll see you next time.